Welcome. Okay, so tonight we're having a presentation on physics. When last year the news came out of the Higgs boson, there was a big brouhaha in the press, and we thought it would be interesting to talk about what really was found. You know, in our culture, science plays an almost mythological role, you know, as this deep, mysterious discipline that certain high priests are able to master. And on the other hand, by contrast, the coverage you see in the press is usually not that great. I mean, they make up things like the God particle, which we shamelessly thought it ourselves, but the truth of the matter, they don't tell you usually very clearly what scientists do. They try to make it understandable, but they often get the opposite result. So we thought we should really invite somebody who knows what scientists do and ask them to let us share in what they do and their experience, also because in reality, some level is, if you remove the technical layer, it's not that hard to understand. And also because scientists have, in a sense, the experience that the more questions you answer, there are always the next question. So there's a deeply human work in which you always face the mystery to some degree. And the way this comes through the work of scientists is very interesting. So for this purpose, we invited two people who are really experts in theoretical physics. The first guy with a great jacket is Giorgio Ambrosio, who is an applied scientist at Fermilab in Chicago. His main research field is in applied superconductivity. That means that he makes large magnets that are used in superconducting magnets for particle accelerators and detectors. He started his career with me at the National Institute for Nuclear Physics in Milan, while we were in college together, but I didn't go to the same institute, where he contributed to the design of the barrel toroid for the Atlas detector at the Large Hadron Collider, which is just a big machine, which is the latest addition to the particle accelerator at CERN in Switzerland. In 1998, he moved to Fermilab in Chicago, where he's a leading researcher in developing superconductor technology for accelerator magnets. He has written and co-authored more than 100 peer-reviewed papers and lectured at CERN and many other leading universities. He's a member of the U.S. National Conductor Development Group and is the chairman of the advisory board for the UCART High-Field Magnet Project. He's also the director of the U.S. branch of Eurosys and a member of our Crossroads advisory board. We'll talk about Eurosys at the end. On the other side is Professor Stephen Barr. He's a professor in the Department of Physics and Astronomy at the University of Delaware. His field of research is theoretical particle physics and cosmology, and in particular the study of grand unified theories, also known as GUTs, I believe, GUT, which are theories that unify the forces of nature, space-time symmetries, baryogenesis, which is the process by which matter originated, and neutrino oscillations. He was elected a fellow of the American Physical Society for his contributions in these areas. He is the author of about 150 theoretical papers in peer-reviewed physics journals. He also writes extensively on the relation of science and religion for First Things, a magazine many of you will know, on whose advisory council he sits. His articles and book reviews have also appeared in National Review, Commonweal, The Weekly Standard, Modern Age, and Public Interest. He is the author of a book, Modern Physics and Ancient Faith, and also a student's guide to natural science. In 2010, he was elected to membership in the Academy of Catholic Theology. Now the first one to speak will be Giorgio. No, Stephen, sorry.
Thank you, Carlo, and thank you all for coming out to hear us. Let's see if there's a convenient place to put this water. Not really. Oh, there we go. Good. So first, let me see if I know how to use this clicker. It's the red button, I presume, for the
Try.
what? Well, that's the laser.
Let's do an experiment.
There we go. In the late 1600s, Isaac Newton proposed his famous law of gravity. According to his theory, objects exert gravitational force on each other across empty space. This is called action at a distance. Even earlier, the great astronomer Johannes Kepler suggested that this was what caused the tides in the Earth's oceans. The moon, he said, was pulling on the waters of the oceans, even though vast distances of empty space separated the Earth from the moon. When you stop to think about it, the idea of action at a distance is pretty astonishing. In everyday life, we're used to things exerting forces on each other, on other things, by making contact with them and pressing on them or pushing them. The idea that one thing can push or pull on another across empty space seems like magic. Indeed, the idea that a heavenly body, like the moon, could affect the behavior of things on Earth sounds like astrology. That's why Galileo rejected Kepler's theory of the tides as absurd. Galileo wrote to a friend, quote, "The one who surprised me the most is Kepler. He was a person of independent genius, and yet he became interested in the action of the moon on the water and in other occult phenomena and similar childishness," unquote. Galileo came up with his own theory of the tides, in which they were due to the motion of the Earth. In fact, this was one of his two proofs that the Earth moved. The history of science is full of ironies. Even though Galileo was right that the Earth moves, his supposed proofs of that were fallacious. In particular, his theory of the tides was wrong, and Kepler's theory that the tides were caused by the moon's attraction was not childishness at all, but absolutely correct. But irony within irony, Galileo turned out to be right about action at a distance. We no longer think that forces act across empty space, as Kepler and Newton believed. We now think in terms of space being filled with fields that transmit forces. Science fiction writers like to talk about force fields, but physicists just call them fields. The idea of fields was proposed by Michael Faraday, that's Michael Faraday there, about 200 years ago. Think about the Earth and a compass needle. According to Faraday's way of thinking, a magnet, and the Earth acts like a big magnet, produces a magnetic field that can be visualized as field lines or lines of force that fill all of space. These field lines can exert forces on magnetized matter, such as a compass needle. A compass needle tends to align itself with the magnetic lines of force. Similarly, electrical forces are transmitted by an electric field. Here's a picture showing how this happens. If one has a positive and a negative charge, so there's the positive charge, that red thing, and the blue thing's negative, the electric field lines come out of the positive charge and go into the negative charge and pull the two charges together as though the field lines were invisible rubber bands. In the mid-19th century, a complete and consistent theory of electricity and magnetism was developed by the Scottish physicist James Clerk Maxwell, this gentleman. And one of the things that emerged from Maxwell's theory is that electric and magnetic fields can have waves in them. So this blue thing over there is a charge. And imagine that these lines are electric field lines emanating from that charge. There are more of them, but I only drew a few. Actually, there's an infinite number of them. And imagine you shook that charge up and down. It would cause waves in the field lines in the same way as if you shook the end of a rope, it would cause waves in the rope. So Maxwell suggested that the light consists of such waves, and many experiments have proved him right. But then came a huge surprise. In 1905, Einstein showed that a certain phenomenon called the photoelectric effect could only be explained by supposing that light is made up of particles. Particles of light are called photons. So it turns out that light, in a very mysterious way, behaves like waves, but also behaves like particles. That is really bizarre. In fact, it almost seems like a contradiction in terms, because a wave is something spread out, like that. whereas a particle is something located at a single point. This mysterious wave-particle duality, as it's called, is not just a feature of light. Quantum mechanics tells us that all waves are particles, and all particles are waves. So we have the following beautiful and unified conception of nature. The basic things in nature, as far as we know, are fields of various types. These fields can have waves in them, as Maxwell pointed out, and then quantum mechanics tells us that those waves are equivalent to particles. And since matter is made up of particles, we see that matter ultimately comes from fields. The electrons, protons, neutrons that make up the matter of your body, for example, come from the electron field, the proton field, and the neutron field that permeate space. On the other hand, fields also give rise to forces, as Faraday pointed out, suggested. So fields are the basis of everything. They're the basis both of matter and of the forces which act upon matter, which push and pull on matter. The circle was closed by another great physicist named Richard Feynman in the mid-20th century. Feynman showed that you can think of forces between two particles as coming from their exchanging so-called virtual particles between them. So the force between two electrically charged particles can be thought of as due to the electric field between them, or as due to electromagnetic waves, that is, particles of light being exchanged between them. So here is a very simple example of what's called a Feynman diagram. You have an electron, two electrons propagating along, and they send photons, these virtual photons, back and forth between them, and that is what causes the force between them. So our present theory of physics consists of two parts. Gravity is described by Einstein's theory of gravity, also known as general relativity. Everything else is described by the so-called standard model of particle physics. In this combined theory, there are altogether 18 types of fields, and thus 18 types of particles. Remember, fields give rise to waves, and waves are equivalent to particles. So these fields come in two basic kinds, called fermionic, over on the left, and bosonic fields. For reasons that are too technical to get into, fermionic fields often act more matter-like, whereas bosonic fields often act more force-like. So under the fermions, we have that E over there is the electron, and there are 5 other types of particles that are kind of related to the electron, and then there are things called quarks. I'm missing a parenthesis here. There are 6 types of quarks that we know of. And then the boson fields, every one of the fundamental forces of nature that we know of is associated with the bosonic field. So there's electromagnetic forces, and there's the electromagnetic field whose particles are called photons. There's the weak force, and that's associated with the W boson and Z boson fields, or particles. There's the strong force associated with gluons, the gravitational force with gravitons, the Higgs force with a field or a particle called the Higgs boson. Now, you've heard that the Higgs field gives many types of particles their mass. I'll now give you a somewhat simplified, oversimplified explanation of how. Consider a heavy object in the gravitational field of the Earth. It has gravitational energy. And the higher up an object is, the more gravitational energy it has. So it takes energy to lift up a heavy object in the gravitational field of the Earth. And if you drop the object, you can release that energy. Similarly, a particle that has electric charge and is sitting in an electric field has electrical energy. That's why it takes energy to pull a positive and negative charge apart. You're increasing their electrical energy. That is the energy they have by virtue of being in each other's electric field. Now, Einstein tells us that energy has mass. Remember his famous formula, E equals mc squared. So if you pull the positive and negative charges farther apart, you change the electrical energy in that system of charges, and thus the mass that's there. So we see that particles interacting with fields, in this case electric fields, can affect their energy, and thus mass. So this is what happens with the Higgs field. Various kinds of particles interact with the Higgs field, and it affects their energy, and they thereby acquire mass. Now it turns out that the Higgs field is a bit peculiar in some ways. All other known fields have some directionality. Electric and magnetic fields, for instance, point along their lines of force. But the Higgs field has no direction. An analogy that might help is temperature. At a certain point in space, there's a temperature. It doesn't have a direction, it's just a number. Okay? And the Higgs field at a certain point in space has a magnitude, which is just a number. It doesn't have a direction. Another peculiarity of the Higgs field is that its magnitude doesn't vary much from place to place. That is not true of other fields, whereas the gravitational field is much stronger near the sun than near the Earth, and the magnetic field is much stronger near a magnet than far away from it. The Higgs field has a nearly uniform value throughout all of space. Moreover, the Higgs field is much more intense than the electric, magnetic, and gravitational fields that one finds almost anywhere. So all around us is this very strong, uniform Higgs field. We don't feel it. For that matter, we don't feel magnetic fields, although some animals do. Some animals feel electric fields also. But even though we don't feel the Higgs field, particles are affected by it. It affects their energy and thus their mass. Of the 18 basic types of particles in our present theory that I showed you a minute ago, at least 11 and probably 14 of them, not counting the Higgs particle itself, derive their mass from being immersed in this pervasive Higgs field. The ones that don't are the photon, the gluons, and gravitons, all of which are believed to be exactly massless. These 18 particles I've been talking about are the basic particles of our present theory. But there are other types of particles that are made out of, composed of these more basic types. For example, protons and neutrons are made up of quarks and gluons. So here's somebody's artist's conception of a proton. And so in those blue and green things are supposed to be quarks and anti-quarks inside a proton. Those curly lines are virtual gluons being exchanged back and forth between the quarks. And so that's what's going on inside a proton. So the proton is a composite. It's not a fundamental particle. It's made out of these quarks and gluons. Now the quarks inside a proton get their masses from the Higgs field. That accounts for only a few percent of the proton's mass. Most of the proton's mass comes from other effects having nothing to do with the Higgs field, such as the kinetic energy, energy of motion of the quarks and gluons inside it. Those particles are all moving around very fast. That has energy. That energy contributes to the mass of the proton. Most of your mass is the mass of the protons and neutrons in the nuclei of the atoms that make up your body. So very little of your mass has anything to do with the Higgs field. Only about 1% of your mass comes from the Higgs field. When and why was the existence of the Higgs field hypothesized? It was back in the 1960s. It happened when people first started to figure out the so-called weak force, or weak interaction. The first force to be discovered by human beings was gravity, which I suppose you'd have to say was discovered by the earliest humans, though people only obtained some theoretical understanding of it in Newton's time. Gravity has an infinite range, which is why it can act across astronomical distances. That's related to the fact that the particle that mediates gravity, the graviton, has zero mass. Remember Feynman's idea that forces arise from the exchange of virtual particles. The smaller the mass of the mediating particle, the longer the range of the force. The larger the mass of the mediating particle, the shorter the range of the force. The next force to be understood well is electromagnetism. This force, too, has infinite range. And the mediating particle, the photon, is massless. In the 20th century, two new forces were discovered whose ranges are very short. In fact, subatomic distances. They're called the strong and weak force. Over the period from the 1930s to the 1960s, the weak force became increasingly well understood. And in the 1960s, it was seen that in some ways this force is very similar to electromagnetism, except that its mediating particles, they're called the W and Z bosons, have very large masses, about 100 times the mass of the proton. Hence the short range of the weak force. W's and Z's, the W and Z particles, are like photons, but very heavy. Now this created a mathematical problem. People did not know how to write down consistent equations for photon-like particles that are heavy, like the W and Z. In fact, it was worse than that. They also did not know how to write down equations for massive particles that can interact by exchanging W and Z bosons. They knew how to write down equations for massive electrons, for example, but not if those electrons can exchange W's and Z's, which they can. This is when Steven Weinberg had a great idea. He didn't invent the idea of the Higgs mechanism, as it's called, but he had a crucial insight. He showed that if you hypothesize the field that we now call the Higgs field, then the W and Z and all the particles that can emit W's and Z's can obtain their mass by interacting with the Higgs field. And this solved the mathematical problem. But in order for this to happen, the Higgs field has to have a very large and nearly uniform value throughout space, because things like electrons have the same mass everywhere, anywhere that you place them in space. So since the particles' masses don't change from place to place, the Higgs field had better be the same everywhere, or nearly the same. Now, why does the Higgs field have this large and uniform strength? After all, as I mentioned before, other kinds of fields, such as electric fields, don't. Their strength tends to vary, to be rather small, and vary a lot from place to place. The reason has to do with how the energy in fields depends on their strength. I didn't mention this before, but fields have energy in them. And for most fields, the stronger the field, the more energy it has. So for electric fields, magnetic fields, and most other kinds of fields, the larger the field's strength, the more energy it has. So if we plot the energy in the field versus the strength of the field, you see that the stronger the field, the more energy. Now, if we may anthropomorphize a bit, all physical systems prefer to have lower energy. That's why a ball will roll down a hill, where its gravitational energy will be less. And this is why most fields prefer, if you will, to have small strength. It takes energy to give them large strength, and so these fields tend to be fairly weak in most situations. The Higgs field, however, has a peculiar feature. Its energy density depends on its strength in the following way. The field wants to have low energy. So here's the energy plotted versus strength, and you see that the lowest energy it can have is not when the strength of the field is 0 over here, but when it has some non-zero strength, which I've indicated by that red arrow. That preferred strength of the Higgs field, in the jargon of the field, is called the Higgs vacuum expectation value, or V for short. Now this is why the strength of the Higgs field is very uniform and very large throughout the universe. It's kind of stuck at this value, okay? And that's a very large value. So what is so important about the Higgs particle in the eyes of particle physicists? In and of itself, the Higgs field is no more or less important than the other 17 basic types of particles that we know about the Higgs particle. Yes, it has some peculiar properties. I mentioned that it has no directionality. The Higgs field has no directionality. That is equivalent to the fact that the Higgs particle has no spin. Its spin is 0. It's only one of the 18 known particles whose spin is equal to 0. But then, the graviton is the only particle whose spin is equal to 2. The Higgs particle is also peculiar in that it's very heavy. But it's not the heaviest particle that we know. It's the second heaviest of those 18 particles. The heaviest one is the so-called top quark. So the Higgs particle has some distinctive properties, but so do many of the other particles. What really makes the Higgs particle special is that it is the last one in the standard model of particle physics, which dates from the 1970s, whose existence has been confirmed by experiment. It has taken a lot longer to produce Higgs particles in the laboratory. Why? A combination of reasons. One is that the Higgs particle is very heavy, so it takes a lot of energy to make one. Remember, E equals mc squared. Second, it is electrically neutral, and also neutral under the strong force. And that makes it harder to produce them experimentally, because most particles that we produce, or that people, experimentalists produce in the laboratory, are produced through their interactions with photons and gluons, through electromagnetic and strong force interactions. And the Higgs field doesn't have those interactions. So there are other reasons as well, but the point is it's very hard to make Higgs fields. It's very hard to know that you've made one if you do, if you have. And it's therefore taken almost 50 years to finally confirm their existence. That's the reason for the excitement in the physics world. Why is it called the God particle? It isn't. Not by physicists. Physicists laugh at that term. It's called that by journalists. The way the name started is this, at least this is what I've heard. A physicist named Leon Lederman wrote a book about the Higgs and other particle physics matters, and he wanted to call the Higgs the goddamned particle. Precisely because finding it had been so difficult. The publisher thought that the God particle would sell more copies. So that's it. At least that's what I've heard. There's nothing in the least bit divine about it. It's no more divine than an electron. It played no role, no particular role, in the beginning of the universe. It has nothing to do particularly with the Big Bang. It's an important building block in the world, but so are the other 17 types of particles that we know about.